We're now going to begin learning different methods of integration, and the first one that we are going to learn is integration by substitution. And this comes in section 5.3 in the textbook. So our goal here is things are going to start getting complicated, and we need some more and more sophisticated ways of finding antiderivatives. So as things start to get complicated, we're going to learn some methods for finding antiderivatives. And so remembering the easier ways to finding antiderivatives, sometimes it would just pop out, like you could just look at it and you knew that this antiderivative, well, we just add 1 to the power, divide by that power, add a constant. And that we can just do mentally. So that's definitely an easier problem. But as we look at harder problems, we might get something that looks more like this. Say you had 2x times the square root of 1 plus x squared dx, and we need to do the antiderivative of this. This is not quite as obvious. We can't maybe do it all in our head. And so we're going to introduce a method called substitution. And I'll give you just a tiny preview of the substitution method. This one lends itself to sort of backwards chain rule. We can almost see how this piece of it was the derivative of this inside here. And so all of these may have come about because of a chain rule. So substitution is essentially undoing the chain rule. So if we're going to undo the chain rule, let's get a teeny bit of practice of refreshing our minds on what the chain rule, just some practice with the chain rule. If you had y equals e to the 3x, then dy dx would be that same exponential function, but now we have to take the derivative of this inner function, and that derivative would be 3. So there's the derivative of that one. Say that we had y equals sine x to the 6th. Chain rule is always used whenever you have a function inside a larger function. And so the derivative of this will be dy dx. Let's see, derivative of sine is cosine of the same thing. Leave it unchanged. But then we take the derivative of the inside, which is 6x to the 5th. Okay, let's do one more. Say that our function was y equaled 1 over 1 minus 6t to the 3rd. And we're going to find dy dt this time. So this is essentially like this expression raised to the negative 1/3. And so the derivative of that will be negative 3. Same inner function. And now our new power is negative 4. We subtract 1. And all of that gets multiplied by negative 6 because that is the derivative of this inner function. Okay, so I feel pretty good about chain rule. Now we're going to go backwards and find some antiderivatives. So we're going to find the general antiderivative of a couple examples. And the first one will be e to the 3x. So we're going to find the antiderivative of this. We need something here that if we take the derivative, we will get this. So e to the 3x is not the right antiderivative, but it's pretty close. We have to think through what would happen if we took the derivative of this. We would get 3e to the 3x, and that's too much. So what if we did something like this? Okay, this should be the true general antiderivative of this guy. Because if we think about taking this derivative, it would be e to the 3x times 3, but we already have a 1/3, so these cancel, and we're left with this guy right here. Okay, so this looks good. This is the general antiderivative. Let's try x to the 5th cos of x to the 6th. So here we can see, again, we're finding the antiderivative, so we're going backwards. We can see that we have some pieces that we want because we need something. Probably it's going to be a sine of something, but then this is going to help us out when we use chain rule to go in to take the derivative of this. So the antiderivative will probably be something like sine of x to the 6th. But if we left it just at that, that's not quite enough, because if we take the derivative of this, we'll get cos x to the 6th, 6x to the 5th, and all we have is an x to the 5th. So we have to compensate for that by putting a 1/6 right here. Okay, so I'm just going to double check this guy one more time. This is, I'm saying, the antiderivative of this guy. So let's take the derivative of this and see if we truly do get this. The derivative of this would be cos x to the 6th times 6x to the 5th, but we have a 1/6 out front, so that cancels, and we do end up with this. So this is the true antiderivative of the thing on top. Okay, last one. Let's try to find the antiderivative of 1 minus 6t to the negative 4. All right, so the antiderivative is going to need to be 1 power greater of this same thing, 1 minus 6t to the negative third, but I'm probably going to need a negative 1/3 out here. And honestly, I'm going to need a negative 1/6 to compensate for when I take the derivative of this, I'll end up with a negative 6. So I'm saying that this, I could clean it up a little bit, but I'm saying that this is the antiderivative of this. Let's double check that. So if I just take this right here, let's see, 1 minus 6t now to the negative 4. There would be a negative 3 out here, but I have a negative 1/3. And then I also have to take the derivative of this, which is a negative 6, but I have a negative 1/6. So it looks like this cancels, this cancels, this cancels, this cancels, and I do end up with the thing that I started with. So this is the true antiderivative. Okay, so I've basically, in my head, used the substitution methods for all three of these examples. You're not expected to, but I just wanted us to get a flavor for how, when we're asked to maybe find the integral of this, we are going to take the chain rule backwards. And we're going to use a substitution method that makes it easier than what I've done here. Right here, I had to keep a lot of things in my head, but we're going to do a more formal method. Before we move on, let's just take a look. Here we were taking derivatives, and here we were taking antiderivatives. When we took the derivative, we had to invoke the chain rule in each of these examples. And here, when we were taking antiderivatives, we had to essentially reverse the chain rule or think through like putting the chain rule back in its place in each of these examples. And that method of kind of compensating for the chain rule each time is the substitution method. So at this point, again, we see the magnificence of the function e to the x. We just love him because you take the derivative of e to the x, you integrate it, you get the same thing, derivative, same thing, integrate, same thing. What an awesome magical function that it just doesn't mess anything up. And it's pretty unique. The only function that does that, it's its own derivative, it's its own antiderivative. It's just awesome. So that was just a shout out to this fantastic function, but because not all functions can be that great, we do have these integration methods. So here essentially we're going to be reversing the chain rule. When you see substitution, you should think, oh, okay, I'm reversing the chain rule. And before I even show you an example of it, I want to talk about when to use it. You know, we're going to go through a few different methods of integration that are helpful, and one of the keys is to know which method to invoke. You would use the substitution method if you can see pieces that would have come from a chain rule. Oops. So when you can see pieces in the thing that you're trying to integrate that would have come from a chain rule, this is when we use the substitution method. It's like you can see a function derivative pair. So a function derivative pair. And the more practice you get, the more you'll start just kind of automatically recognizing these. So we're going to go through an example of the chain rule, and then we'll kind of give a formal explanation of it. So say we were asked to find the integral of x cubed cosine of x to the 4th plus 2. This is definitely one that we just can't look at and spit out what the answer is. But we do see, right up here, we say, you know, the substitution method is when you see a function derivative pair. And I kind of do see that. I see this sort of inner function x to the 4th plus 2. And the derivative of this would be 4x to the 3rd. Well, I don't have the 4, but constants, honestly, usually you can make up for. So don't get hung up on constants. The important thing is I do have an x cubed, which is an important part of the derivative of this. So I see this sort of function and mostly derivative pair off by a constant, but that's okay. We'll compensate for that. And so this is how I know that for this integral, I'm probably going to use the substitution method. And so it looks like this. I'm going to pick that function that has its derivative sitting there. That's what I'm going to let equal to something I call u. So we're going to say let u equal x to the 4th plus 2. Then just taking the derivative of that, I know that du dx is 4x cubed, right? Okay, this is good because I'm just going to let this be u. I have a x cubed, and I'm going to do a little bit of manipulating here. So this, I'm going to say du is 4x cubed dx. And then I'm actually going to divide both sides by 4. So 1/4 of du is x cubed dx. And the reason I move things around is because this right here, those are pieces in the integral I was given. And so I'm trying to transfer everything into u's at this point. And so this is really helpful because instead of saying that I have an x cubed and a dx in the integral, I'm going to say all of that is just equal to 1/4 du. So I rewrite my integral as the integral of cosine of u, because remember that this part I just said was u, and then I actually, this and this piece of it are just equal to 1/4 du. So I'm going to put the 1/4 right here and the du over here. This is now an integral that I have no problem with. This is an easy integral to evaluate. This will be sine of u, the 1/4 just hangs out, plus a constant. Okay, so I'm not quite done yet, but this integral was way easier to figure out than this integral, and so that was a good substitution to make. I now go ahead and put back, instead of using u's, I'm going to go step back into x's. So this is equal to 1/4 sine of x to the 4th plus 2 plus c. And this is my final answer here. So again, we just look for that. Hopefully we can find a function derivative pair. You may be off by a constant, but you can compensate for that. Okay, so now we'll take a look at the very general description of what integration by substitution is. If you're given the task to find the integral of f prime of g of x times g prime of x dx. So essentially we have, I mean, you can see that the chain rule was done. Like this is after the fact of a chain rule happening. What you're going to do is let u equal this inner function. So here you have a function derivative pair. And so we're going to let u equal gx. So this will be a u now. And this is going to become the integral of f prime of u du. And because of the fundamental theorem of calculus, this is equal to f of u plus c. We then go back to our original variables, f of g of x plus c. So what we've done essentially is recognize there's a chain rule that happened, make a really clever substitution that makes the integral here much easier than the integral over here, find that integral, and then put everything back into the original variables. Okay, so remember that we're going to look for a function derivative pair, and then we're going to let u equal that function. Again, we may have to compensate a little bit with a constant that's that we may have to deal with or undo, but constants are usually very workable problems. If we have essentially the right other pieces, then we definitely can make it work. Okay, so here we have, we're going to do this problem, and I want you to already start thinking about what kind of substitution you would use. And so the question is, do you see a function derivative pair? And you may be off by a constant, but that's okay. And so you've probably already realized that, okay, awesome, this is a function right here, and most of its derivative, it's just off by a constant, is sitting right here. So we definitely want to let u equal that function, then du dx equals 2x. Then we can say du equals 2x dx. You won't, and we can then say that 1/2 du equals x dx. This is really helpful because we have an x dx right here and right here. So those pieces are in the original integral, and we can now just translate them to du's. Honestly, you'll stop doing some of these middle steps, and as you work more examples, you'll just kind of go from here to here. Okay, so we are going to rewrite this integral as e to the u, and then we have a 1/2 du. And the integral of that is just 1/2 e to the u plus a constant, and that will be 1/2 e to the x squared plus a constant. And that's the solution. This is the integral that we were asked to find. Okay, this is our next example. We're asked to find the integral of natural log of x over x. Okay, before we go through the next example, I want to go over this thought. This is from the book Range by David Epstein. He says, one of those desirable difficulties in learning is known as the generation effect. Struggling to generate an answer on your own, even a wrong one, enhances subsequent learning. So as we go through these examples, you've seen some examples already from me for the substitution method, but as we go through, we're going to go through several more examples. I highly encourage you to pull out a pen and paper or pencil and paper and attempt the problem on your own before you see me do it. This will greatly enhance your learning of this topic. There's nothing quite like struggling to find an answer on your own before you see it done by somebody else. So take a minute to try this one on your own. Go ahead and pause the video. As you try it on your own, productive struggling is going to result in better learning. Even if you don't get it right, just the attempt and forcing your brain to think through what you would do is going to make it better learning, and in the end, it's going to be more lasting and really more efficient through that struggle. Okay, so you've paused the video and you've done the problem on your own, and either you got it or you didn't, but either way, just stopping to try it on your own is really going to help you. Okay, when I look at this integral, I can't immediately tell what the solution should be, but I do see natural log of x and then essentially a 1 over x here. So that in my mind triggers, oh, there is a function derivative pair here. And if I were to say the function was natural log of x, then its derivative is 1 over x, so it's sitting right there. So I'm going to let u equal natural log of x, and du dx will equal 1 over x. So that's awesome. Now I can, so du equals 1 over x dx. And so I can rewrite the integral as the natural log, I'm sorry, u, which is just the natural log of x, and then I have du is right here. So u du. That's a much easier integral to evaluate than this guy. And so the answer to that is just u squared over 2 plus a constant. And I go back to my original variables and the original function. And that is natural log of x squared times 1/2 plus a constant. And that is the solution to this integral. Next example is to find the integral of 1 over cosine squared t squared of 1 plus tangent t dt. This is definitely one that I couldn't just pull out of my brain. I'm going to use the substitution method. I do see a function derivative pair here. So definitely take a minute, pause the video, try this one on your own. Let u equal something, a function that maybe you see its derivative here as well, and see if you can evaluate this integral on your own. So remember to look for a function derivative pair. Okay, so you've taken some time to do this problem on your own, and maybe you got stuck, but maybe you had some ideas that you at least tried. Maybe you got the whole thing. Usually with substitution method, the two pivotal moments are, first of all, does the substitution method apply? And the second pivotal moment is, what should I let u equal? In this problem, I see a lot of trig things going on. I see a cosine squared, I see a tangent, and somewhere in my memory bank, I remember that the derivative of tangent is secant squared. And so this doesn't say secant squared, but it is a cosine in the denominator, which is like a 1 over cosine squared t, which this is a secant squared. So this probably is going to be the original function, and then its derivative is essentially sitting right here. So I'm going to let u equal not just tangent, but this whole thing here. We would not want a 1 to have to hang out all by itself, and the derivative of 1 nicely is just 0, so you know, it's not going to cause any problems when we go to use this as the derivative. So I'll let u equal this whole thing inside of the square root function. I don't take the square root function, I just take this inner function. And so u is going to equal 1 plus tangent of t, and then du dt equals secant squared of t. And so I have my substitution. I can rewrite the integral as the integral of, let's see, I have a 1 over the square root of u, and then I have all of this is my du. It's exactly du. And that's a really easy integral to find. It's just essentially u to the negative 1/2 du, and so that will be u to the 1/2 times 2 plus a constant, which is 2 times 1 plus tangent of t to the 1/2, or the square root, plus a constant, and that is the integral that I was looking for. Okay, this is our next integral to evaluate, and honestly, it's not quite so obvious that the substitution method should even be used here, because it looks like, you know, say that I let this equal my original function, the derivative of that is 2x. I do have an x up here, but unfortunately I have this guy hanging out, which is causing a problem. I don't really want a 1 plus, I just want the x. And so it's not quite so obvious that substitution method is going to work here, but I'm going to try it. And so we'll say, why don't we let u equal 1 plus x squared, and then du dx is equal to 2x. Okay, and so if I try to rewrite my integral, then I have, let's see, the denominator is u, and this is a problem because I don't have an x dx, I have a 1 plus x dx. So unfortunately, this is not going to work, this substitution is not going to work. So we tried it, but that's not going to work. We have to think a little bit more creatively here. So we will end up using the substitution method on this problem, but there's some sort of pre-work that we have to do. Can you see anything before we use the substitution method that we could do to this problem? Well, one thing we could try is actually splitting up this fraction. We could take 1 over this denominator and then x over this denominator and just split it up into two different integrals. That's totally legal to do. And if I do that, this second integral actually does blend itself really well to the substitution method. I have a function and then I have mostly its derivative right here. The only tricky thing is what's going on with that first integral. If I take the integral of 1 over 1 plus x squared, well, that is actually a derivative of something. So we mine our mind way back in the way back and try to remember that this is actually the derivative of arctan or inverse tangent function. So this problem is awesome because it's going to require us to use the substitution method, but it's also going to require us to remember the derivative of arctan. That's not uncommon that one problem will contain a few different approaches. I mean, this problem definitely does that, so we shouldn't be shocked when we see it. I've split up this original integral into these two integrals, just splitting up the fraction, and we've recognized that the antiderivative of this is actually just arctan or inverse tan of x, and in this we're going to use the substitution method. It lends itself really nicely to substitution. And if I use the substitution method, I'll let u equal 1 plus x squared, and then du equals 2x dx, and so 1/2 of du will equal x dx. And so I can rewrite that second integral as 1 over u and then a 1/2 times du. And so we think for a minute, what is the antiderivative of 1 over u? Is this a power rule thing? No, it's not. It's the antiderivative of this is natural log of x. So this will equal 1/2 natural log, not x, of u plus a constant, and that equals 1/2 natural log of 1 plus x squared plus a constant. So that's the second half of the integral, and this was the first half. So the integral, the whole thing, solution will be tan inverse of x, and technically this had a constant, when we took the antiderivative, but we're going to just combine the constants over here, plus 1/2 natural log of 1 plus x squared plus c. This is the evaluation of that integral. Okay, at this point I want to review one thing that we should keep track of and make sure that we remember. As soon as I put limits on my integration, that turns into a different problem. So these two problems are very different. Well, not totally different. I mean, in each case you're trying to find an antiderivative, but essentially this top one, when you have limits of integration, this is called a definite integral, and this is called an indefinite integral, or maybe sometimes it's called a general integral. And the solutions to each of these will look very different. The solution to this will be a number, the solution to this will be a function. And so if I wanted to find the solution to this, I know that it's x to the 4th over 4 evaluated from 1 to 5. This ends up being 156. So importantly, this integral that started looking really similar to this one is asking you to find a number. But this integral, this is an instruction. It's saying find the antiderivative of x to the 3rd. So this is an instruction to you, and the instruction is find the antiderivative. And that would be x to the 4th over 4 plus c. So as soon as we have a problem that has limits of integration, we're looking for a number. If you don't have any limits of integration, you're looking for an antiderivative. And so I just wanted to make sure that we're keeping all that straight. The next example we'll look at is an application, a model for the basal metabolism rate in kilocalories. I'm pretty sure that's kilocalories per hour of a young man is R of t equals 85 minus 0.18 cosine pi t divided by 12, where t is the time in hours measured from 5 a.m. What is the total basal metabolism of this man? 0 to 24 of R of t dt over a 24-hour time period. In this problem, they've given us a huge hint that this is what we want to find, but this honestly would have been a totally legal problem if that hadn't even been explained. Because of the wording, we should know that that's what we're looking for. So look at the wording of this problem. A model for the basal metabolism rate. I had to look up what that is, but it's your resting metabolism rate. You probably all knew that, in kilocalories per hour. And then we have this function. So this is the rate at which somebody is burning calories just by resting. For a young man, this will output the rate when your function is a rate like this, so we have a function over time, and we're measuring in kilocalories per hour a metabolism rate. That's the vertical axis. And they're asking for what is the total basal metabolism of this man over 24 hours. We're looking from 0 to 24 of essentially the integral of this function. So we want to, the end result will be how many kilocalories were burned in that 24 hours. So the wording itself tells us we're looking for the integral of this function over 24 hours. Nicely, they gave us that that's what we're looking for, but honestly, you are at a point where you should recognize that that's what you're looking for. So I was kind of interested in knowing what this function looked like, so I went ahead and graphed it. And this is, this axis, the horizontal axis is time, and the vertical axis is measuring that rate, R of t, which is the basal metabolism rate in kilocalories per hour. So it looks like it's not a constant thing, that at certain points, and this is from t equals 0 to t equals 24. So at different times you're burning at a higher rate than at other times. But essentially when they're saying over 24 hours how many kilocalories were burned, we're looking for, we're trying to add up all of these calories, and it goes down because this is not even 0. So we're looking for the integral of that function from 0 to 24. This is the integral that I want to evaluate, and I start thinking, okay, how am I going to evaluate this? And since we've been talking about substitution method, of course that's coming to your mind. What would we let you equal, though? Well, as I look at this, I probably honestly want to split this up into two integrals, this one and this one, because this first part is a really easy integral to evaluate. This one is actually going to be one of the easier ones we've seen. We just kind of have a wonky inner function here. But you can see what the derivative of this inner function is going to be. It's just going to be pi over 12, which is a constant. That's actually one of the easiest applications of the substitution method. So let's go ahead and split this up into two integrals, and then we'll let u equal this inner function. Its derivative will just be a constant. We can always compensate for constants. But this is not an integral we really want to tackle just in our head. So that's why we're going to use the substitution method. So I've split up the integral. This is going to be an easy integral to find. I've pulled this 0.18 out front, and I'm essentially just looking for the integral of cosine of this slightly complicated function inside. So this would be a great time for you to attempt this problem and see this is a definite integral. So in the end, we're going to come out with a number. It would be great for you to try it and see if you come out with the same number that I do. So pause this video and try to evaluate both of these integrals on your own. This one is just a straightforward integral. This one you'll benefit from using the substitution method. Okay, to evaluate this, I'm first going to tackle this guy right here just because I'm really anxious to use the substitution method. So I want to let u equal that inner function pi t divided by 12, then du equals pi over 12 dt. So that means that dt is going to equal 12 over pi du. So the second integral is negative 0.18. I'm going to pause right now on my limits of integration. We'll come back to that. And I have cosine of u. And then I need a 12 over pi du. That is what dt equals. And this is a pretty easy integral to evaluate. This, for the first time, we have to think about what happened to our limits of integration. This is when t equals 0 to 24, but we're not dealing with t's anymore. So one way we can handle this, there's two different approaches, and we'll show one of them here and one of them later. But here we could retranslate each of these numbers into u's. This is t equals 0, but we're now in u's. So if t equals 0, let's see, that would be a 0 times pi, which is 0, divided by 12, which is 0. So actually that limit stays as 0. But as soon as we let t equal 24, t equals 24 over 12, which is 2 times pi, then our new limit, now that we're in u's, our new upper limit of integration will be 24 twelfths times pi, which is the same as 2 pi. So our upper limit of integration turns into 2 pi. Now this integral is fairly easy to evaluate, negative 0.18 times 12 over pi. And then the antiderivative of cosine of u is sine of u, and we're going from 0 to 2 pi. So I'm looking at these limits of integration and what they're going to go into. They're going to go into a sine function. I happen to know that sine of 2 pi is 0 and sine of 0 is 0. So this actually is all going to just turn into 0 here times a constant, and that part will just be 0. So this equals 0. Okay, so we turn our attention back to the first part, which we've been ignoring. And this part never got into the u-substitution. We didn't really need a u-substitution for this part. It's a very straightforward integral. And so the antiderivative of 85 is 85t from 0 to 24. We still have the limits of integration on t because we're still working in t's. And this is 85 times 24 minus 85 times 0. And 85 times 24, that number will be 2040. And that is actually the solution to the integral because all of this, the second half turned into 0. So what does that mean? That means that the basal metabolism, the total basal metabolism of this man is 2040, is it kilocalories? Okay, I want to talk about the limits of integration in that problem for a minute. We had started with, this was a piece of the problem, and then we made that u-substitution where we had cosine of u du, and there was a 12 over pi, and then we realized the limits of integration needed to change from 0 to 2 pi because our variables changed. And for part of that problem, we found the antiderivative. So for a problem, you can evaluate that antiderivative with the limits being changed to, like that u equals 0 and u equals 2 pi. Or if you don't want to go through the step of changing your limits of integration, at this point, you can actually just transfer everything back to t's and use the original limits of integration. So we could have said that this equals 12 over pi sine of pi t over 12, and use those original limits of integration, 0 to 24, and you would have ended up with the same thing. This all ends up being 0 anyway. So it's fine to use the original limits of integration as long as you take everything back to the original variable, or you could have used the limits of integration that we found for u and just found the solution to the problem, never having translated it back into the t variable. Either way, that's one of the things with definite integrals is you can stay in u and just evaluate the number. With indefinite integrals, if these aren't here, you always have to go back to the original variable that you were working with because they're asking you for an antiderivative to this function, and the u's would make no sense. I want to end with these two examples. They're a little bit more difficult just because some extra letters are introduced, but they're actually fairly easy substitution method problems, but we just have to keep track of things. I do want you to try both of these problems on your own before you look at the solution. I'll give you a few hints though. Because we're taking the integral with respect to x, everything else that isn't an x is treated as a constant. So this a is a constant, this b is a constant, this is the same a and same b, they're constants. So the only variable in this problem is x. Down here, the variable that we're taking the integral with respect to is t, little t. So this one's a little tricky because you have a big T also. That big T will be a constant. And it looks like constant. This is the only variable. Even this alpha is a constant. You will use a u-substitution in each case. This one is going to result in just a function. This is an indefinite integral. This one will result in an expression that represents, an amount. So try both problems on your own. As you do try these on your own, you will find that productive struggle will enable you to learn things better. I always tell students that you have to give calculus the respect it demands. It is not something that you can just watch someone do and pick up and learn and you've got it. You have to struggle a little bit. So this is one of those great opportunities for you. So you've solved or attempted the first one, attempt that second one as well. So on this problem, if I was just faced with it, I would look to see if I can find a function derivative pair. I see definitely some inklings of it. I see that there's an x cubed here and an x squared here. I see that there's an x here and then just a constant here. So it doesn't fit exactly, but it looks like maybe the derivative of this is somehow related to this. Hopefully it's just off by a constant. So I'm going to attempt it by letting u equal this thing inside the radical. So we're going to let u equal 3ax plus bx cubed. And then du dx, okay, I have to remember that x is the only variable, everything else is a constant. So the derivative of this, because x is the only variable, the derivative will be 3a. Du dx is 3a plus, again, x is the only variable, so the derivative of that will be 3bx squared. 3bx squared. And So I look at what I have up here. It's not exactly what I was hoping for, but it's very close. I have an a plus bx squared, a plus bx squared. It looks like if I factor a 3 out, then I can get very close to what this looks like. So I'm going to say, okay, du equals 3 times a plus bx squared dx. And then if I say 1/3 du equals a plus bx squared dx, I have all the pieces that I need. This right here is going to take care of this guy and this guy, and then I'll just have a square root of u in the denominator, and that will end up being an integral that's fairly easy to integrate. So now I'm just going to stick everything in with u's. So I have in the denominator square root of u, and then I have a 1/3 du. That's pretty easy to integrate. It's like a u to the negative 1/2, so I'll add a power and multiply it by 2. Plus c, take everything back into x's. 1/3 times 2 is just 2/3 times 3ax plus bx to the third to the 1/2 plus c. So this is the solution to that. Okay, so I'm anticipating that this one will take a little bit more room. I mean, after all, we have to go back and put in limits of integration. So I'm giving myself a little bit more room. This one, honestly, is not a terrible u-substitution. The only complicated thing is this inner function. But if little t is the only variable, then the derivative of that inner function is just going to be a constant. We use a u-substitution because there's no way I can keep track of all this in my head. But the u-substitution is very straightforward. So we're going to let u equal that inner function, 2 pi little t divided by big T minus alpha. And then du dt is just 2 pi over big T. This was just a constant that went to 0. And so du equals 2 over pi big T dt. I don't really have anything like this in here, so I'm just going to move this constant over so it makes it easier on my brain to make the substitution. Big T over 2 pi du is the same thing as dt. Okay, so I have all my pieces. I've got what I want u to equal, and I'm going to put in for dt this expression here because they're equal. So my integral becomes sine of u. Nice, awesome. And then dt is the same thing as large T over 2 pi. And then I have a du. Okay, now the question is limits of integration. So honestly, I did the last example where I changed the limits of integration to be u's. I'm going to actually keep my limits of integration as t's, and then we will reevaluate, substitute back in little t's in here. So I'm going to, for right now, I'm just going to say, okay, I'm going to still let little t equal t over 2 and little t equal 0, even though I'm working in u's at this point. When I do the integration, I'm going to go back to little t's. So I'll go ahead and do the integration, and it is negative cosine of u, right? Because the derivative of negative cosine will be sine. I have this, let's move the negative over. I have this t over 2 pi, and I'm going to let that equal negative t over 2 pi cosine of 2p little t over t minus alpha. And now that I'm back in little t's, this is going to go from 0 to big T over 2. So I can already tell that, the substitution was not that hard. The hardest thing in this problem is making sure I'm copying everything correctly, all of the variables, and switching things back into the t variables correctly. But now I'm at this point. I just need to evaluate all of this at these limits of integration and find the solution. So I've gone ahead and pulled this out front, and then I'm just going to evaluate this at my upper and lower limit of integration. Just got to make sure I put everything in where it's supposed to be. Cosine of 2 pi, and now my variable little t is this big T over 2 divided by big T minus alpha. That's the first upper limit, minus cosine of, it's going to be 0 minus alpha, negative alpha. And now I'm going to clean it up. And I've got negative big T over 2 pi times, okay, so cosine 2 pi times big T over 2. These 2's will cancel, these t's will cancel, and I just have pi minus alpha. So cosine of pi minus alpha minus cosine of negative alpha. And so this is our solution. It doesn't look that beautiful, but it is a solution that only contains, some constants. So if we knew what big T and what alpha were, we could evaluate this for a number. Okay, just a quick recap of the substitution method, some of the big ideas. We are basically reversing the chain rule using this method. When we're trying to decide whether to even use the method, we look for function derivative pairs. And if we find one, that function is usually what we're going to let u equal. Be careful in a definite integral to keep track of the limits of integration. You have two ways you can do it. You can keep everything in u, but then you have to translate the limits of integration to what the u variable is doing. Or after you find the antiderivative, you can go back to the original variable and just keep the original limits of integration. Also keep in mind that sometimes the substitution method is only part of the problem. We saw this example where we actually had to split it up into two different integrations, and the first integration wasn't even using substitution method at all. It was just having us remember the antiderivative or the derivative of arctan. All right, awesome.